10H, Dr. Bevilacqua here. What I wanted to do was go over quiz 3. I have some notes here from our graders where they pointed out some of the problems that happened with the quiz, and so I'm gonna be reading these on one screen and kind of going through here with a pen on the other screen and go through what I think some of the problems and misconceptions were. Um, so on the first problem, it seemed like there were some mixed up signs that ended up with the wrong signs for W and for delta E and delta H. And so just make sure that you get that right. So when you see here, for example, that a liquid is being boiled, well then you know that delta V is positive, and so down here, because this is positive, you know that the work is going to end up being negative, and you can see that in the final answer. Um, you know the heat's going into the system, so the heat's going to be positive. And delta E here is Q plus W, Q sub P plus W sub P. You know, delta E is path independent, so you could certainly add together Q and W from any path, certainly the constant pressure path. And so what you're doing here is you're just basically taking this answer and putting it in here, and then taking this answer and putting it here, and then you're adding those together. The other thing to keep in mind is units. So what you'd like to do is get work or have to do is get work and heat into the same units to be able to add them together. So, you know, we're given the heat in kilojoules here, and so of course we need the work to be in kilojoules, or we can't add two numbers together unless they have the same unit. So we can see here that work comes out in liter atmospheres, and so now we need to get it into kilojoules, and we can see that the that the quiz provides the conversion for us. We just divide through by liter atmosphere, so we can get that there's 0.101 kilojoules per liter atmosphere. Okay. The second problem seemed to cause a bit more difficulties, and one of the main problems here was this 1/2 on the hydrogen. You know, so I'm going to give you a different way to do this, and that is to just go through and multiply through by 2 so that you can get rid of the fraction. And so now you can effectively have a 1 here in front of the hydrogen. Okay, so once you do that, then for delta H0 of formation, for delta H, we take the delta H0 formations of all the species, and so we start with the products and drop in the value for sodium hydroxide, and that one is right there. And so if you're going to do it the way I have it set up there, there's now 2 moles of that, so you would multiply through by 2. And then you add to that delta H0 for formation for hydrogen, but that's 0. Then you go to the reactants, subtract those out, so it's 2 times the one for water. So you subtract out 2 times minus 285.8 is plus, and then sodium is 0 because that's in its standard state. So you add these two guys together, and you'll effectively get the right answer. You won't need to do this, but everything will be times 2 because of the way I have it set up, and so you get the right answer here. And that number, minus 367.6, is the number you would put right there, and that would be the number for that reaction with 1 mole of hydrogen, because I've multiplied through by 2. Okay, so now we need delta E. We just take this very familiar formula, number of moles of gas change, so we put that in there. We look at how many moles of gas change, and you can see that it is 1 minus 0. This is the only gas right here, and so delta N is 1 right there. We multiply it by R, multiply it by T, and then we need to get the units into the same units that are on delta H. Delta H here is in kilojoules, and so we need to get this thing into kilojoules, so we divide by 1,000. Not all the units are written out here, but please go through and do that, and you'll see that that converts us from joules into kilojoules. And when you do the math, then it will come out to minus 370. And again, this goes exactly with how it's written right there. So that's the number that would go up into there. Okay. Moving on to part B. And so in this particular example now, it draws on the reaction above, and it gives you a defined amount of sodium being added to a beaker of 1 liter at a certain temperature and pressure. And then basically what you need to do is go through and figure out what the temperature rise in the calorimeter is going to be. We know the temperature is going to go up because it's an exothermic reaction. Delta H is very negative. So that's the first thing, is when I'm going to sit down and do this problem, I'm going to remind myself, I'm going to write myself a little note. This should go up. And then I'll see if that turns out to be true in the end. So Q equals MC delta T, or the book uses MS delta T, and so this is the mass of the calorimeter right there. Here's the specific heat of water with the right units, and then here's your delta T, and then that has to be equal to the heat generated. And so you have to remember that you need to take the number here of 183.8 per mole of sodium, or you could take minus 367.6 up here, and that would be, now is the way I have it here, for every 2 moles of sodium, which comes out to 183.8. But don't just use this number. You can see that the units aren't going to work. If you go over on the right, you can see the units are in terms of kilojoules, not kilojoules per mole. So we need to get rid of moles. How do we do that? Well, we multiply by the number of moles of sodium, and you can use standard conversions to go from those grams to the number of moles of sodium. So now the two sides have the same units. The left is kilojoules, right is kilojoules, and then you just go through and solve for delta T, and then you can get T final by adding delta T to T initial, add it to the 25, and you end up with your 33.76. On question 3, let's see. Most of you did pretty well, and the most commonly missed one was B, the entropy of the gas. And so basically an ideal gas is expanding into a vacuum. This is sort of similar to the gizmo that was shown in the reading. And so there's a stopcock here. We start out with gas molecules just on the one side, and then we open this up, and then you know what's going to happen. The gas molecules are going to rush over to this side. And so there's more positions, and so there's more disorder, there's higher entropy. And just a reminder, you can create higher entropy by having the molecules more spread out, having more particles, and then highest entropy is gas, followed by aqueous, followed by liquid, followed by solid. Okay. And then in question 4, let's see. There seemed to be a lack of conceptual understanding of enthalpy. Most of you didn't justify your answers in terms of bond strength, intermolecular forces, or energy. And a lot of you got that this state here with the gases was the highest enthalpy, but you justified it by stating there's more moles of gas in the first case. And that's not why there's higher enthalpy. Enthalpy is all about bonding, not about disorder. And so you have to look at the bonds all the way through. And so what you're doing here is you're trading the bonds in hydrogen and oxygen for the stronger bonds here in water. Remember, these are polar covalent in water, which is stronger. They have that electrostatic component. And then as we move down the hill this way in terms of enthalpy, so getting lower enthalpy means getting stronger bonding. So stronger bonding. And where's that bonding coming from? Well, we already got the strong covalent bonds in the gas, but then the water molecules make intermolecular bonds, and so they make bonds in liquid. And then as it continues to go down, then we have lower temperature, and of course that's lower enthalpy when we lower the temperature. That was the example that we saw last Friday. And there was some confusion, like, can you really have a gas at room temperature? Can you really have steam at room temperature? Of course you can. The way you get it is by having low pressure. And so it's possible. And also, can you have water at 0 degrees? Yeah, sure you can. When you have ice water, that water is at 0 degrees. Okay. And then last was number 5, and you guys did quite well with this question, but some people did not connect the change in the number of moles of gas with delta V, and that led you to conclude that P delta V was 0. So there's a change in the number of moles of gas. There's 2 plus 1 on the right, and so that's 3 on this side, and there is 2 plus 1 on this side, and so there is 3. Sorry, there is 1 on this side. This is a liquid, and there's 3 on this side, so there's 1 minus 3 right here gives us minus 2. And so we can see that whatever delta E is, delta H is smaller by minus 2 RT, so that allows us to get this as the right answer. Okay, hope this was helpful. Thanks for listening. Bye-bye.